Hi there, folks. Today we're looking at conditions of rhombuses, rectangles, and squares, and really we're kind of doing the same thing that we've been doing, where we kind of look at the converse of each of those properties that we've already looked at. So we've looked at a couple properties for rhombuses, rectangles, and squares. Now we're going to use those same properties, but in reverse, okay? So we had a property that said, hey, if we have a rhombus, then the diagonals are perpendicular. So now we have this property that says if the diagonals are perpendicular, if it's a parallelogram and the diagonals are perpendicular, then it's a rhombus, okay? So kind of working backwards to get the opposite thing. Before we were given it's a rhombus, and then we figured out that that means we have perpendicular diagonals. Now we have a parallelogram with perpendicular diagonals. That means it's a rhombus. Same thing with the next guy. We had one that says, hey, if it's a rhombus, then the diagonals bisect the opposite angles. So now if we have a parallelogram where the diagonals are bisecting the opposite angles, now we know it's a rhombus, okay? It's the same thing as our properties that we looked at, but in reverse. Now we're working backwards to say, oh, now I can say this is a rhombus. So proving that that thing is a rhombus. Likewise, the property we have for the rectangle, if it's a rectangle, the diagonals are congruent. Now we have, if I have a parallelogram where diagonals are congruent, now I know it's a rectangle. So it's that idea of using the converse of each of those properties to prove that this thing is that particular shape, okay? And so if we look at something like this guy, these guys, it's the same thing as what we were doing when we looked at the properties, but we're just answering that question from a different perspective. See, before it would say something like, hey, this is a rhombus, find x and y. All right. Now we're saying, if x and y equal this, that would make it a rhombus. Okay, so it's literally the same question, but from a different perspective. So if I look at something like this guy, it says, what would the value of each of these be to make this thing a rhombus? Okay, and so if I look at this first one, if this were to be a rhombus, then the diagonals would have to be perpendicular to one another, meaning each of those angles would have to be 90 degrees, okay? So if I wanted this to be a rhombus, then each of these would have to equal 90 degrees. So the 2y minus 2 would have to equal 90 degrees, and the x plus 52 would also have to equal 90 degrees, okay? And if I solved each of these over here, I'm going to add that 2 to each side, and then divide by the 2. Over here, I'm just going to subtract that 52 from each side, and I get a 38. And that's it. And so just like when I was answering these questions before, if it told me this was a rhombus, I would do the same thing. I would say, hey, if this is a rhombus, x and y have to be this. Now, the only difference is how I express this answer. I'm saying, hey, if x was this and y was this, then this thing would be a rhombus, okay? Literally the same question, but asking it from a different perspective, okay? If I look at the next one, again, I don't know that this thing is a rhombus, but if I wanted it to be a rhombus, then that diagonal would have to bisect those opposite angles. So that means that the 6x minus 2 and the 4x plus 8 would have to equal one another, okay? If I wanted this thing to be a rhombus, these would have to be congruent. So the 6x minus 2 would have to equal the 4x plus 8. And I'm not saying that they do equal one another. I'm saying that if they did, this would be a rhombus. Okay, so again, same question, different perspective. I subtract the 4x from each side. And now here I'm going to add the 2 and divide by the 2. And I get x equals a 5. Okay, so again, it's more like I'm just asking the hypothetical question. The hypothetical question just happens to be the same thing I was answering when I talked about the properties of these things. Okay, if I look at something like this guy, it says given BE equals a 5a plus 3 and CE equals a 7a minus 5. Find the values of A for which ABCD is a rectangle, okay? And I'm not saying ABCD is a rectangle. I'm saying if it was a rectangle, what would A have to be, all right? So if this thing was a rectangle, the diagonals would be congruent, all right? And so you have to be a little careful here. Notice it doesn't give us the entire diagonal. It only gives us half of the diagonal. But we know that in a parallelogram, the diagonals bisect each other. So if these two entire diagonals are congruent, if BD is congruent to AC, and they're each being bisected, it means that these two pieces are congruent. Okay, but it also means that all four of these pieces are congruent. So this works out okay. Just make sure you're aware of what the question is giving you, because at some point maybe I'll give you BD and then I'll give you something like CE. And so CE is going to have to be doubled to equal BD. And so kind of just think about what it's giving you. Don't just assume and set these things equal. In this one, yeah, BE and CE are congruent if this thing is a rectangle. So if I want this to be a rectangle, I'm going to set these equal to one another. Okay, so I set them equal to one another. I'm going to solve. I'm going to subtract the 5a. I'm going to add the 5. And I'm going to divide by the 2. And so once again, I'm not saying this thing is a rectangle, but if a was a 4, then it would definitely be a rectangle. Okay? All right, in this one, I want to find the values at x and y that make a, b, c, d a square. And once again, I'm not saying that this is a square, but what values would I need in order for this to be a square? Again, same question, but we're asking it from a hypothetical perspective, okay? And the other thing is this: we didn't have any theorems that dealt with squares here, so we have to remember that a square is really just a rectangle and a rhombus together. So it has all the properties of a rectangle and all the properties of a rhombus. So its diagonals are perpendicular. Its diagonals are congruent, like the rectangle. Its diagonals are bisect the opposite angles. Okay, so it has all those properties of the rhombus and the properties of the rectangle combined. All right, and so if I look at this guy. Once again, we're in the same situation where it's also a parallelogram, so the diagonals bisect each other. So all of these little pieces would have to be congruent in order for this thing to be a rectangle. So all those pieces have to be congruent in order for it to be a square. So I'm going to say that the 2x plus 4 has to equal the 3x minus 5. And then I would subtract the 2x from each side. I would add the 5. And I get x equals a 9, okay? So x would have to equal a 9 in order for this thing to be a rectangle, but now to make it a square, that rectangle also has to be a rhombus. So when I look at those that diagonal and those angles down in the bottom, there are two options here, okay? One, we could say, hey, it's a rhombus, so just going straight rhombus, these things have to be congruent, so they have to equal one another. So the 3y plus 30 has to equal the 6y plus 15. Okay, and then I would subtract the 3y from each side. Subtract the 15. Some really fun numbers in here. And divide by the 3, so I don't need that 3 anymore. Come on, Mr. Jansen, get your head in the game. So I get y equals 5. The other option here is if you know that you want this thing to be a square, that means it has the properties, it's a rectangle and a rhombus. So not only does that diagonal bisect that angle down there, but you also know what that whole angle is. If you want this thing to be a rectangle, then this guy has to be a right angle, which means if that's being bisected, each of these has to be a 45-degree angle, okay? So instead of setting them equal to each other and solving, you could just take one of these and set it equal to 45. If you do the 6y equals 45, 6y plus 15 equals 45, you subtract the 15 and get a 30, divide by the 6 and you still get a 5. If you did the 3y plus 30 equals the 45, you would subtract the 30 and get a 15 and then divide by the 3 and still get a 5, okay? So make sure you understand a square is a rectangle and a rhombus at the same time, so it holds all of their properties together. Okay? If we look at this guy, it says given triangle AB and triangle CDE are isosceles with bases AB and CD. E is the midpoint of AC. I want to prove that parallelogram ABCD is a rectangle, okay? And so to prove that this thing is a rectangle, I either have to find that the definition holds true, that each of these angles, A, B, C, and D, each of those large angles on the outside is 90 degrees. That would prove it by the definition. Or I would have to just prove that the diagonals are congruent and use that theorem to work backwards, okay? The fact of the matter is, proving the diagonal is congruent is typically easier and typically faster and less steps than trying to find each of those angles being 90 degrees. Okay. And so if I look at this thing, if I start to kind of map this out before I write my proof, triangle AB is isosceles with base AB. That means that these guys would be congruent. Okay. That's an isosceles triangle. Triangle CDE is isosceles. So these guys would be congruent. Okay. And then it says that E is the midpoint of AC. And so if you know that this guy is the midpoint, we're going to find out then that AE and EC are congruent. So we're kind of thinking about that in our minds. And so we already have that those are congruent. And hopefully you're thinking about, okay, transitive property, then I'm going to be able to say that ED is thrown into the mix as being congruent. And then I'm going to have the entire diagonals congruent with a little bit of segment addition. So let's kind of write this out in terms of our proof. Let's get my statements and my reasons going. Again, I was just talking about, what do we know about this thing? Where's this thing going to lead? And sometimes it helps just to kind of verbalize, all right, this is what I know. Can I get from point A to point B? Can I get to this thing that I want to prove? And now let's justify it step by step. Okay. So triangle AB, triangle CDE, are isosceles. I'm just going to leave it at that. I'm not going to write out the base thing. Okay, we already know which ones the bases are. And then E is the midpoint. Okay, and all of that is just given to us. And even though this is a relatively easy proof, when you think about the connections here, and it might be easy to kind of see, it's a little bit harder to kind of get all of this down on paper. So let's start with triangle AB and triangle CDE being isosceles. Let's state the really obvious thing, and that's using what an isosceles triangle is. Let's say that, hey, you know what? AE is congruent to BE. And then likewise with the other triangle, DE is congruent to CE. And that's just what an isosceles triangle is. That's our definition of an isosceles triangle. All right. The other piece of given that it gives us is that E is the midpoint of AC. And we know what the midpoint means. It means it cuts that thing into two congruent pieces. So right away, I can say that AE is congruent to EC. And that's the definition of the midpoint. And from here, here's where it kind of gets a little dicey. Most of us are probably want to look at this and go, oh, BE is to AE and AE is to EC, so BE is to EC, and call it our transitive property. Technically, we should have these as measurements first, so I should convert all this to measurements because of the definition. And so there's coming out some of those little nuances that your teacher might not want you to follow. They might just have you go right to AE equals EC. I'm going to go ahead and do the measurement thing only because I know we're going to need segment addition at some point, and that has to be in terms of a measurement. So I'm going to say this. I'm going to state everything that I just stated, but I'm going to state it as equal signs and not as segments. So the length of AE equals the length of BE. The length here of DE and CE are equal. And the length of AE and EC are equal. Okay? And, this is helpful in a couple ways. One, that's kind of where my transitive property works, but also segment addition. And I talked about that as we were kind of working through this thing before we started. That's the definition of congruent. Okay, things being congruent means their measurements are equal. So now with all that said, I can say things like this. I can say that, hey, that means that, BE is equal to CE or EC. Okay, I can say those are equal because BE was to AE, AE was to EC, so BE is to EC, and that's my transitive property. And so when I kind of think about that, at this point, if I come back up here and relabel this thing, I proved that AE and EC were the same. So I can put a slash through there. And then I made that connection from EC to ED. We said that those are the same. So now I see that all of these things are the same, okay? And so if I kind of think about that for a moment, if all of those things are equal, I could say something like this. I could say that, and again, we could really stretch this out, all right? I could say something like AC is congruent to itself, or AC is equal to itself. That's our reflexive property. And then I could say that AE plus EC is equal to AE plus EC because of segment addition. And then I could use substitution. So, kind of keep that in mind here. There's quite a few routes we could go. I guess we could stretch it out. So, here's like the nitty gritty technical aspect. I could say that this is equal to itself because of the reflexive property. And then once again, I could say, what is that? AE and EC. And that's our segment addition postulate. And now I can start replacing these pieces. I could say something like this. Oh, counting is hard. 8. I'm counting down all of a sudden. I could then replace these pieces. So right now I have AE plus EC. Well, actually, I could go ahead and replace that. Well, I'm going to have to replace it in the next step anyway. And so I could replace like the AE with the BE. And I could replace the EC with the DE. Okay? And now I could say, that's substitution. And then from here, I could just rewrite these back as these entire segments. AC equals, well, BE DE gives me segment BD. And see, we're just working backwards using our segment addition postulate again. And now we could go back to congruent. Hey, these guys are congruent because their measurements are equal. That's the definition of congruent. And now I have the diagonals congruent, which means this thing is a rectangle. So if it's a parallelogram with diagonals congruent, then it's a rectangle. And as I'm writing that down, I don't know if I included that up here, that this thing was a parallelogram. It says prove parallelogram. And so this piece of the given was kind of stated in the prove statement, but we could kind of add it here with the given that this was a parallelogram. And so I've really stretched this thing out with all the tiny itty bitty little details. Your teacher might let you cut out half of these, okay? And so they might let you just leave it in terms of, congruence and in terms of segments to do your segment addition postulate, all right? And if they do that, it means you would cut out a bunch of these steps, okay? Well, really, you would cut out these two. You would cut out like this step, okay? And then you would just do this with, segments above each of them and the congruent symbol, okay? And they might even let you cut out something like this step and go right to this guy, okay? And so keep that in mind. It really depends on how picky your teacher wants to be with some of these things. If we're getting every single nitty-gritty little detail, we could probably cut out some of these, okay? In terms of my perspective from a reasonable justification, we can make a leap on some of these and kind of cut out some of these little steps, okay?